Okay, so welcome everyone. My name is Erick, as he already mentioned. I'm a developer experience engineer, and I'm going to talk about something I found really cool, which is the Rust programming language, and also about a recent addition to Infobip, which is our Rust SDK. So first, we will see how Rust improves developer experience and how it helps you have more quality in your software. And also, we will move on to see what are the good design aspects of a library and how we improved our own SDK with those. So why Rust? As some of you may know, Rust has been the most loved programming language in the last 6 years. But why is that? That's what we will try to find out today. So to start, let's think about why we created programming languages and compilers in the first place. So this is how we made programs back in the 50s with assembler. And as you can see, this is incredibly difficult to write and incredibly difficult to read. But it's very, very easy to make mistakes with it. Then things started to evolve. And in the 70s, we had C, which was already much better than assembly. You got some nicer syntax and some help with errors and optimization, but that wasn't enough. And a lot of things have improved and have been changing since the 70s. So now we have much cooler things like this. As you can see, this code is very easy to read. Actually, the other previous examples do the same thing as this, which is just counting the duplicate letters in a string. And well, you can see that this is like English. It's just test to lowercase, then you get all the characters. You request a special iterator that can find the duplicates, and then you just count the amount of elements in that result and return it as a 32 unsigned integer. So we created programming languages and compilers to improve developer productivity, mainly in 4 ways. One is to make the language easier so that it's similar to English or to mathematics. The second reason is to enable developers to run their program in different types of processors. And the third reason is that we can make optimizations in the process of translating that language to machine code, and also you can find a lot of errors in that process. And it's in these last 2 items where Rust really shines, because it produces really fast programs, and it also helps you avoid a lot of the mistakes that you can make. So why Rust then? Why is Rust especially liked by the industry and by the community? Because it helps us fallible humans. We make a lot of mistakes when we are new programmers, and as the years go by, we just make a lot of mistakes, but much more complex ones. So we need more help from our tools. So Rust is to developers like Yoda was to the Jedi, because it's in your back telling you how to make safer code, and it teaches you delayed gratification, because at the beginning it's very difficult, it's tough to fight the compiler, but over time you get more and more productive, and it's actually very easy, or it's pleasant to use the language after some time, and it's productive. Oh, what's happening? Okay, coming again. So I'm going to use the keyboard better. So we were... This is not made with Rust, obviously. So Rust improves software quality, and mainly it does in 2 main aspects, which is by creating safer software and more efficient software. And apart from that, you also get very nice tools, very nice abstractions that allow you to write elegant code that can do difficult stuff. And it's low level, so you can control the details of what you're doing. And last but not least, it's a very loved language, and that is important because when you love how you do things and what you're doing, you end up being much more productive and with producing higher quality in what you do. So Rust finds a lot of errors, and it's finding them earlier. At the moment that you are writing your code, you get a lot of help from the IDE thanks to the strong type system that it has. And when you have other languages, it's you who has to find the errors, and probably you have to find them in runtime after you have to do a deployment and a configuration and a lot of stuff. So you lose a lot of time trying to do that, and it's possible that even you have to do that like at 4 a.m. and it's a mess. So basically, Rust achieves safety in several ways, but the most important is that it introduces more order into your code. It lowers the chances of errors by being very strict with some rules that disallow having multiple owners of data. So you can't have like a lot of side effects. Basically, it gets you under more control over references, and so that you can have only one writer and one reader, or maybe one writer and multiple readers, but it's much safer. And also you can have immutability, so once you set data, it doesn't change, and you avoid side effects. And another interesting way in which Rust is safer is by making you aware of what can fail. So you have to keep in mind what can go wrong. And in Rust, when a function can fail, you must be explicit with how it can fail. So every function that fails must return a result enum, which is like a Schrodinger box. So for example, if you had a function to get a cat from an online store, it may be that the cat arrives dead or that the cat arrives alive. So you have to handle both cases. In the case that it's dead, you have to write some specific code so that you handle that error. Or in the case that it's alive, well, you just play with it. So if it compiles, it probably works, and that's something really cool when you are programming. And it's something that you don't get with other languages, because you already filtered a lot of the possible mistakes. So the second great deal about Rust is that it's fast. This is a rough comparison of several programming languages and the programs written with it. And as you can see, C is still the fastest. And there are some other very popular languages like Perl and Python, which are like 10 to 20 times slower. So why not use C then? Because apart from being the king of speed, it's also the king of bugs. It's really, really easy to make mistakes with C and also with C++. And that's what makes Rust shine, because you just get the high speed of a low-level language, and also you get all the modern stuff and safety that comes with it. So an interesting way in which Rust achieves this speed is by ditching the garbage collector. As some of you may know, when you have a garbage collected system, your program has to run a second program in the background that is catching the garbage. And that happens at a random time, so you don't know how it's going to behave. You don't have guarantees of whether that memory is going to be actually freed or not. And you have to actually stop your program, free memory, and then continue. So that removes a lot of the speed. And when you have no garbage collector, you just get determinism and faster programs. And well, what I personally like about Rust is that both low level and high level. So you can do whatever you want with it. In the side of low level, you get things like memory pointers. You get the fact that it runs embedded, that it compiles to actual assembly, so you don't have an intermediary virtual machine or something introducing more overhead. And you get things like customized drop memory. And on the side of high level, you get things like automatic memory freeing, functional patterns inherited from languages like Haskell, like pattern matching or combinators and iterators. From the object-oriented world, you get things like generics and traits, which are like interfaces. And Rust comes with its own set of nice things, which are making multi-threading easier and safer. And also, there's a thing called hygienic macros, which allow you to extend and surpass the barriers of the syntax of the language. So that's a cool thing that Rust learns from a lot of other languages, and it has a different context because it's actually being adopted, and it provides the industry and the community with an opportunity to improve software. So, for example, we had C, which was faster, but it's really error-prone. We have had languages like Haskell, which it has nicer abstraction maybe, but it's slow in adoption. It doesn't have a good performance, and the ecosystem of tools is not so great. We have some languages like APL, which have very nice syntax, very concise, but the same problem. It doesn't have the same performance or the same ecosystem. And we even have some languages that give you stronger security contracts, but it's the same. They don't have the same context. And thanks to all this cool that Rust gives you, a lot of cool stuff is being made with it. So, for example, recently Meta announced that they are going to use Rust for backend services and for command line interfaces. And they are giving their developers first-class support with the language. And another big news recently is that the Linux kernel is actually adopting a second language for its development. Finally, someone convinced Linus Torvalds to include a second language after 30 years, so that speaks about the language. And also, now big companies are investing in Rust, like Amazon, Microsoft, Google, and now even Infobip. And there are some cool projects like WebAssembly and WASI, which allow you to run Rust in a lot of containers and communicate with operating system in a safe way. And also in the world of Web3 and blockchain, we have Definity's Internet Computer, which is implemented in Rust and allows you to create decentralized applications with Rust, and Solana, which is also implemented with it. And now in terms of developer experience, you get very nice tools. The main one is Caro, which is the project manager, which allows you to do everything from creating a new project, building it, managing dependencies, publishing what you do, all in one place and in a very simple way. And also the Rust compiler itself is awesome because it gives you very nice error descriptions, and also it gets a lot of help from the IDE thanks to its rich type system. Then you get some tools like Rust format and Clippy, which allow you to improve the standards of your code. And that avoids you a lot of fights with your colleagues over code style, for example. And we also have very nice support with the main IDEs, like JetBrains has a very nice plugin. VS Code also has Rust Analyzer as well as NeoVim. And you can get some nice help also from AI generators like GitHub Copilot. And also, Rust is very versatile. Thanks to things like WebAssembly, you can run in embedded devices with custom hardware. It can run on x86 or ARM, laptops, servers, and it can even run in the front end. It can pair with JavaScript and run in a browser. Also, it has a very cool community that is growing fast, and the core team that develops Rust is improving the language every couple of months in significant ways. And even though we have that fast-paced improvement, we don't have problems with versions and all that because Rust guarantees that versions are compatible between them. So, for example, if you have a project that has the 2018 version of Rust, it can have dependencies that use the 2021 or the 2015, and you don't have any hassles. Then now we will move on to how we built our Infobip Rust SDK. So you can get started with both Rust and the Infobip services. So first, we will see what are the design aspects of a good library. Basically, a good library should save time. It should be easy to use, and it should provide you with a wide range of use cases that are helpful for you. It should also have a neat organization so that it's easy to find things, and it should be easy to develop so that it can keep improving and also be fast. So in the aspect of saving time, if you were to communicate directly with Rust to the Infobip API, you would have to find a nice HTTP client. You would have to model errors and payloads, and you would have to clutter your project with code that is not belonging to your use case. So instead of doing all of that, we provide you with a simple package that does all of that for you, and even some more cool things. So to make it easy to use, we try to keep everything very low in terms of code. So this is an example to send an SMS. As you can see, it's basically only 4 lines. You just create an SMS client with some configuration. Then you just create a message that already has the destination and the text. Then you create a request body, which is attached with the message that you just created. And then you just call the endpoint, send, and that gives you a response. So we also try to make it neatly organized. So what we do is we have mainly 3 modules, one called API, where we have all the endpoints, one for configuration, and one for models, where we have all the error definitions and all the payload definitions. And then we have a subdivision of per Infobip channel, like for one submodule for SMS, one for WhatsApp, and the same for the models. And that enables us to use a very cool feature from Rust, which is called cargo features, which allow you to only compile what you need. So instead of having to compile all the code in the library, you just compile the specific feature that you want. Instead of, if you are going to use, for example, SMS, you don't have to compile email, WhatsApp, and all other things that we support. So we are not giving you time to slack off like this too. And another cool thing is that we have validated payload models. So for every piece of data that you are going to send to the API, we have an object, which is in Rust is called struct or enum. And these are easily serialized so that you can send them as text over the network or store them. And another cool thing that you get is that we have value validation. So you can make sure that all the fields in one of these objects has the correct type of data and the correct type of value. And you get good responses from the API. Another thing to make it easy or convenient is that we have flexible ways to build these payloads. For example, in this case, we have a minimalist version of how to create a message object by calling a new constructor, and then you set the fields that you need. The second way to build these models is by just parsing JSON directly or XML or whatever format that you have. And the third way is by calling what is called in Rust the true constructor, which is allowing you to have better immutability so that you can set all your data in one sentence and then keep that reference or that binding immutable. Another cool thing is that we have nice models for errors and handling of them. So this is related to the Schrodinger box that I was mentioning before. When you have a function that can fail, and in this case, calling an API is I/O, so it can fail. You have a map of what is success and what is an error. So for every kind of success, we have a special type called SDK response with the special data for that kind of call. And for errors, we have this special enum, which can handle any kind of errors that can happen. So for example, if you have an HTTP error, a validation error, a serialization error, or in the case of 400 and 500 types of errors, we have the API request error. So you get very nice details of what's going on with your API calls. Another cool thing is that it's thoroughly documented, so that makes it much easier to use the library without having to look at too many examples or stuff like that. We are using the official way of documenting Rust library, which is docs.rs. There you can find a description of every function, what it receives, what it returns, and some description of the function. And the cool thing about the Rust system is that the examples that we are providing there are actually compiled and tested as part of the test suite of the SDK. So you can just copy and paste, and you can be certain that it will run because it's compiled. And that's actually special and makes it easier for us. Now, the way in which we are achieving a fast SDK is by enabling asynchronous behavior. So if you have to do multiple calls to the API, you don't have to wait and call them in sequence. You can call them in parallel and even do other things, and that saves you a lot of time. And also, to make it easy to develop, we are leveraging code generators, specifically the OpenAPI generator. So for all the payloads that we have, we just feed the generator with the OpenAPI specification. Then we did a cleaning of that generated code. We gave it a nice design. And after we had a good base of code, we used AI to generate a lot of the boilerplate. And that gave us a very nice and maintainable SDK. And last and most importantly, this library should work. So now we are going to see it in action. So okay. So do you see the code? I think it's there. Yeah, okay. So this is the basic example to send a WhatsApp message. In this case, it's only 3 lines of code. As you can see, it's only creating a client that is configured from the environment. Then you just create a request body, which contains the sender information, the destination, and also the text that you want your user to read. And then you just call the send text method of the client and get a response. And then we just print that response. So if we run this, you see that it's compiled and it runs. And you get a nice 200 OK response with some details about the state of your message. And as you may have seen, yeah, here's the message I got, 1729, yeah. So that's on time, and yeah, that's all I had for you today. But this is messed up. Yeah, that's all.